Hello friends, today I'm going to show you how to find GCD of two integers using Euclidean algorithm. First of all, let us see what is GCD. GCD is the greatest common factor. Or highest common factor. HCF. So in our school days, we used to factorize the numbers. For example, if I consider two integers 24 and 36. Okay, if I want to find out GCD of 24 and 36, then we would factorize them like 2 into 12, 2 into 2 into 6, 2 into 2 into 2 into 3, and 36 as 2 into 18, 2 into 2 into 9, 2 into 2 into 3 into 3. And then we would consider the common factors. This is the first one I'm getting, first two, which I'm getting as a common factor. So then another 2 is available here. Here also it is available. So second 2. Then in 24 there is 1, 2, but in 36 there is no 2 available. So we will not consider this. Now there is a 3, which is common to 24 and 36. So we will consider that. And thus 12 is the GCD of 24 and 36. This was our school method. There is another method which is called as Euclidean algorithm. If we are dealing with very big numbers and we cannot easily factorize them, then we can go for Euclidean algorithm. So let us see how it works. So I'm considering the same example, which will help you to understand the algorithm easily. So the basically Euclidean algorithm says that you divide the bigger number by the smaller. Okay, so for example, so here we are going to apply division algorithm. Okay, that means dividing the bigger number by smaller number. So here between 24 and 36, 36 is bigger, right? So we will divide 36 by 24. So it is 24 into 1 plus 12. Now, so let me call 36 as B and 24 as A. So here B is equal to A times something Q plus R. And R is not equal to 0 right now. So what we will do now in the next step, replace B by A and A by R and continue this process till we get remainder equal to 0. So we have to continue this step of replacing B by A and A by R till the remainder is 0. So right now 36 is equal to 24 into 1 plus 12. Now I am writing the second step. So I am replacing now 36 by 24 and A by or 24 by 12. So 12 into 2 plus 0. So right now I am getting 2 steps only. Let me write the 2 steps again. 36 is equal to 24 into 1 plus 12. 24 is equal to 12 into 2 plus 0. And in the second last step, where you get remainder is 0, just above, you have to look at the remainder, and that remainder is nothing but your required GCD. We have seen that using factorization method, GCD of 36 and 24 is 12. And here also we are getting it as 12. Now let us consider another example which will help you to express GCD also as a linear combination of those two integers. So after Euclidean algorithm, we are going to see how to express the GCD in terms of the given numbers. So let me consider the example. Find GCD of 3927 and 377 and express it as D is equal to, so let us call GCD as D, for example, and then 3927 times M plus 377 times N. So we want to basically represent or express GCD as a linear combination of the given integers. So let us apply Euclidean algorithm. So 3927 is greater than or bigger than 377. So I'm dividing 3927 by 377. So you get an obvious integer multiple here, 10. 377 into 10 is 3770. Plus the remainder is 3927 minus 3770. And so the remainder is 157. Okay. Now, so this was my B, this is A, and this is R. Now, the next step, I'm going to replace B by A, that is 3927 will be replaced by 377, and 377 is replaced by 157. So 157, 150 into 2 is 300, 157 into 2 is 314. So an obvious integer multiple, we are getting it as 2 plus, now 377 minus 314. So that is 63. Okay. Then now again, this is my B, this is my A, this is my R. So we will replace 377 by 157 and 157 by 63. So 63 into 3 would become 189, which is greater than 157. So again, obvious multiple is 2. 63 into 2 is 126. 157 minus 126. 157 minus 126. 31. I'm purposely doing these subtractions over here, though they are very simple. Sometimes you get confused. Now again, this B 157, I'm going to replace by A, that is 63, will be equal to 31 into 2 plus 1. 31 into 2 is 62, 62 plus 1. Now again, so still I'm not getting a remainder equal to 0. So I'm continuing this. Now I will replace 63 by 31. 31 is equal to, and 1, I have to consider 1 here, 1 into 31 plus 0. So remainder has become 0, and I'm going in the second last step. And this is nothing but the GCD of 3927 and 377. So these are the steps we need to understand. And here, see, there are 1, 2, 3, 4, 5 steps. Now our next task is we want to express GCD, that is 1 is the GCD, as a linear combination of 3927 and 377. And in fact, we get infinitely many pairs of this expression, but let us try to find out one at least here. So we will have to go back to the expressions many times to express it as a linear combination. We cannot do it in one step. Okay. So we will start with the second last step. Okay. So what I'm doing, I'm just I just want to duplicate this page. So I have duplicated the page and now I'm just zoom. Okay, I just want to refer to these things. And so I am keeping this as a reference. Okay, let me just increase it a little bit. Yeah. Oh, sorry. So now let us see how to express 1. So I'm going to this second last step. Okay. 1. 1 is equal to. Now as 63 is equal to. Okay, let me write the second step once again. I will just write this as 63 is equal to 31 into 2 plus 1. And therefore, I can just write 1 as 63 minus 31 into 2. What we are going to do is 1 by 1, we will make substitutions for these integers from from Euclidean algorithm steps, and we will try to bring 3927 and 377 in the expression one by one. Now I have got 63 and 31 right now. So I will see what is to be substituted for 63. Now for 63, I will write 377 minus 157 into 2. Okay, this is my 63 minus. Now for 31, I'm using this expression. That is 157 minus 63 into 2 will be 31. And this whole thing into 2 again, we have to write. So let us simplify it. So 377 minus 157 into 2 minus, now this is 157 into 2 again. And this minus will become plus 63 into 4. So now I have got 377 in my expression. I don't want 157 to occur and 63 also to occur. So for 157, I'm going to use this star expression. So let me write 377 as it is. And for 157, I'm going to write 3927 minus 377 into 10. And this whole thing into 2, I have to read 10 with. Okay, yeah. Sorry, before that, let us simplify. We are getting 157 into 2 into 157 into 2. So that makes minus 157 into 4 plus 63 into 4. And now I will make use of this star expression for 157. So 377 minus, for 157, I'm writing 3927 minus 377 into 10 and the entire thing into 4. Plus again for 63, I'm going to write this expression A. So for 63, I'm writing 377 minus 157 into 2. And this entire thing into 4. Okay, so this becomes 377 minus, now let us simplify. So it becomes 3927 into 4. Now this minus makes it plus 377 into 10 into 4. So that becomes 40. Then plus here 377 into 4. And minus, this plus and minus becomes minus 157 into this 2 and this 4, I have to multiply. So that becomes 8. Now I want 377, 397 in my expression, but I don't want 157. Okay. So for 157, again, I will make substitution. So let me just rewrite it, simplify it. So I am getting 377 into 1 plus 377 into 40 plus 377 into 4. So that makes, and all are plus. So that makes 377 into 1 plus 40 plus 4 minus 3927 into 4 minus 157 into 8. Okay, so that makes 377 into 45 minus 3927 into 4 minus 157 into 8. So I am just left with 157 right now. So I will again substitute from my star expression, I will substitute 157. So let me just duplicate this page and I will yeah. So let me just I just want the last one expression to detail with. This is my last expression. So every problem will be different as the Euclidean algorithm steps would be different. So right now 1 is equal to 377 into 45 minus 3927 into 4 minus 157 into 8. And from this star expression, I have this 377 into 45 as it is, minus 3927 into 4 as it is. Now, in place of 157, I'm going to again substitute from this star, that is 3927 minus 377 into 10 and the whole thing into 8. So this again becomes 377 into 45 minus 3927 into 4 minus 3927 into 8 plus, now this minus and this minus becomes plus 377 into, I have to take 10 into 8, 18. So now I have what I want. I want only 377 and 3927 to appear in my expression. So I'm just rewriting their integer multiples. So this is 45 and this is plus 80. And minus 3927 into 4 plus 8. So that becomes 377 into 125 minus 3927 into 12. So if I want to write 3927 first, then it will become 3927 into minus 12 plus 377 into 125. And one can always verify whether this gives us correct answer. 3927 into 12 would be 47124. This is minus and plus I want to verify 377 into 125. So that will be okay, let me just calculate it quickly. So 377 into 125. Three 77 into 125 gives me 47125. So 47125 minus 47124 is 1. That means our integers are correct. Okay, so this is the expression. So every problem has its own logic, as I always say, because the steps, the number of steps you require, the integer multiples, the remainders, all are different. And therefore, so let us have a quick recap. We have seen how to find GCD using Euclidean algorithm. So I started with GCD. GCD is the greatest common factor or highest common factor. In school days, we used to do it using factorization technique. Common factors are collected and their product is nothing but GCD. Now, in Euclidean algorithm, we divide the bigger number by the smaller number and we go on replacing. That means we apply division algorithm and the bigger number is termed as B, smaller number is termed as A, and the remainder is termed as R. Then we replace B by A and A by R gradually since till we get remainder equal to 0. And I consider this particular example 3927 and 377. So these are the steps of Euclidean algorithm. We stopped here as our remainder became 0. So these two numbers are relatively prime to each other. There is nothing in common between them. In common as one is the GCD. Okay. So these are the steps, and we use back substitution technique here. We start with the second last step. For expressing 1, we started with 1 as 63 minus 31 into 2, and gradually we brought the integers using the previous steps, and we stopped where we got only 377 and 3927 in the expression. And we also verified that these products are giving us our GCD as 1. So I hope you like this video, and I hope the concept of GCD makes it easier to understand. See you soon with more new concepts. Thank you.